What's going on, math people? All right, we are back, and we're going to go tonight. We're going to be covering logarithmic and exponential equations, as well as exponential growth. All right, so let's jump straight in. All right, check it. Just recall, a log is an exponent. Logs are exponents. Keep that deep in your mind. Anything that's equal to a log is an exponent. So, in this case, here, since y is equal to this log, that's telling us that y is an exponent. Therefore, the conversion that's taking place shows you there that y is an exponent. Okay? Alright, so all that is just the recaption of the conversion process, converting from log to exponential. That's all that is. And then it has this quick little corollary or theorem or whatever you want to call it. And basically it says if log base a of m equal log base a of n, the only way that can be true is if m and n equal each other. If all of this is the exact same, the only way this equal sign can hold true is if m and n equal each other. Alright, let's get rolling into some examples. Alright, it wants us to solve a logarithmic equation. Solving logarithmic equations is we do that by converting. So we're going to run through this quick little conversion process. What's the base? Identifying the base. Base is 3. So we have base 3. What's the exponent? Anything that equals the log is the exponent. Equals x. So if you want a quick little shortcut, you could cover up the log with your finger or whatever and swap x and 6 and you'll get the same thing. 3 to the 6 is something. That's 81 times 3 would be 243. That's 3 to the 5th, I think. And then 243 times 3, I think it's like 729 or something. And so, I don't have my calculator on me, so let me just do a quick little. We have 9, we have 2, we have 7. Alright, 729 equals x. Alright, let's keep rolling. Oh, we have log base 2 of x plus 2 plus log base 2 of 1 minus x equals 1. And I think that's what it is. Alright, so anytime logs are separated, anytime two logs are separated and they have the exact same base and they're separated by an addition sign, we can combine those into one log using, that's right, sum to product rule, or product to sum. So we have x plus 2, log base 2 of x plus 2 times x minus 1 equal to 1. And we will simplify that side. We have log base 2 of, and that's supposed to be 1 minus x. I have to catch my little errors. But I'm only human. Alright, so we have negative x squared plus x plus 2 minus 2x equal 1. Alright, so we're going to rewrite this, and then it will give us log base 2 of negative x squared minus x plus 2 equals 1. Alright, now we want to solve this by converting the log to an exponential. So we have negative x squared minus x plus 2 equals 2 to the 1. And finally, simplifying, we have negative x squared minus x equals 0 when we deduct 2 from each side. Right here, we deducted this 2 from each side. And factoring out a negative x, that leaves us with x plus 1. So we have solutions here. We have negative x equals 0 or x plus 1 equals 0. That will give us potential solution of x equals 0 or x equal negative 1. Now, with logs, you want to make sure your stuff makes sense. So you want the expression, once you plug those solutions back in, to be greater than 0. So we plug 0 back into the original. We have 0 plus 2. So let me write it on the screen so you can see what I'm talking about. Checking your solutions. Check x equals 0 first. All you have to do is plug it into your original stuff. That's 0 plus 2 and a 1 minus 0. Both of those are greater than 0, so they're good. X equals 0 is a solution. And then checking the negative 1, plugging it in. We have negative 1 plus 2 and 1 minus negative 1. Both of those are greater than 0, so we're good to go. Solutions are x equals 0, x equals negative 1. Alright, another quick little recollection. If you have an exponentials, bases are the same, then the only way those two exponentials can be equal to each other is that the exponents equal to each other also. Alright, so the base here is a. The exponents on each of those is u and v. So let's jump into an example. Alright, so we have 5 to the x minus 2 equal to 25. 25 can be rewritten as base 5. What exponent can 5 be raised to give us 25? That's right, the second. So now, notice we have the bases are the same. Since the bases are the same, now we can take the exponents and set them equal to each other and solve for x. So we have x equal 4. The domain of exponential functions is all real numbers, so you never have to check the validity of your solutions for exponential equations. You're welcome. I believe what you're trying to say is thank you. All right. Let's keep rolling. So we have 3 to the x equals 7. Now what to do when the bases cannot be rewritten to represent either base? That's when you pull out that natural log function, pulling out the juice. When the bases cannot be rewritten the same, pull out the natural log. So we're going to take the natural log of both sides. Taking the natural log of both sides. Now we can apply power to factor. So we have bring that x down, and we have x natural log of 3 equals natural log of 7. We want to get x by itself. We're solving for x, so we're going to divide each side by natural log of 3. And voila, x equals natural log of 7 over the natural log of 3. So anytime the bases cannot be rewritten as the same, pull out the power of the natural log. Natural log. Keep rolling. And we have 5 times 2x, 5 times 2 to the x equal 3. Alright, well, we're going to get this exponential by itself first, so we're going to divide each side by 5. And now we have 2 to the x equals 3/5. Question: can 3/5 and 2 be rewritten so that they have the same base? The correct answer is no. So what are we going to do? Somebody said natural log. Natural log. Doing the natural log to each side, and we have natural log of 2 to the x equals natural log of 3/5. So we have power to factor, x natural log of 2 equals natural log of 3/5, and solution. X equals natural log of 3/5 over the natural log of 2. Alright, now we're going to mosey on over to 6.7 to grab those exponential financial models with compound interest and continuous compounding. So first we're going to jump into compound interest. Compound interest, notice we have FV, that stands for future value. Future value. Alright, PV, that stands for present value or principal investment. R is your interest rate. Interest rate. And you want to convert the percent to a decimal. N is the number of times compounded. Number of times compounded per year. And T is the number of years. Alright. Number of times compounded per year. Those keywords at the bottom that I am underlining in, let's say, green. All of these words represent N. Annually, semi-annually, quarterly, monthly, daily. All of those represent N. So if it's annually, that means N is 1. Semi-annually, N is 2. Quarterly, 4. Monthly, 12, and so on. Alright? So let's jump into an example. Alright. We have... before I jump to this example, let me just say this. The hardest part about this section is putting the proper amount of parentheses inside of the calculator. That is the hardest part. People usually get calculator errors because they miss a parenthesis. So whenever I write this out, I'm going to write it out exactly how it should appear in the calculator. Alright? And I'm talking about a scientific calculator. I'm not talking about some little standalone calculator. A little Yankee ding, a little pew pew. Anyways, investing $1,000 at an annual rate of 10% compounded annually, semi-annually, quarterly, monthly, and daily will yield the following amounts after 1 year. So investing $1,000 at an annual rate of 10%. Let's see here. That's telling us that's our principal investment. So the principal investment is $1,000. And it says the interest rate is 10%. So we said we need to convert that to a decimal, so that is 0.10. And it first said it wants us to hit every mark. I'm only going to do this one time. I'm not going through every mark. N equals annually, that would mean N equals 1. And for the number of years, it said after 1 year, T equals 1. The only thing that's missing is future value. And we can see that when we set up the formula, future value equals. Now, this is how it will be entered into the calculator. You will put your present value, 1000, hit your multiplication symbol, open a parenthesis, 1 plus the interest rate, hit your division symbol, and that's 0.10. Let me write that better. I don't want anyone confused. Plus 0.10 divided by the number of times compounded, which is 1, and that is equal to, I'm sorry, not equal to, close the parenthesis, hit your caret symbol to get you an exponent, open you another parenthesis for that exponent, put in the exponent up for the n, hit your multiplication symbol, put in your number of years, hit your multiplication symbol, close your parenthesis, hit your equal sign. After hitting your equal sign, you would get $1,100. Alright. Now let us keep on keeping on. Find the principal needed now to get the given amount. That is, find the present value. So this problem is saying find the present value. Alright, so if it wants us to find the present value, that's telling us that the future value should already be inside of your problem. It says to get, that means we don't have it as something you're going to receive in the future. So your future value is $1,000. And after 1 3/4 years, you want to make sure you convert all these 3/4 years and whatnot. You want to make sure if this was in months, you want to convert that months to years. Alright, so we have n is the number of times compounded. It said compounded daily. That's 365. And t is 1 3/4, which is the same thing as 1.75. And R is the interest rate, which is 4%, which is the same thing as 0.04. And we're trying to find out what the present value is. So recall that the formula is future value equals present value times 1 plus R over n raised to the n times t. That is the formula. Alright, so here's the trick. If you want to find present value is equal to, alright, present value is equal to, let me get this little ugly thing out of the way. The future value, get my pencil now, future value times all of that good stuff raised to the negative n times t. And that'll give you your present value. So practice putting it into your calculator. Just make sure you have your parenthesis. So we have present value equals 1,000 times 1 plus 0.04 divided by, some of you can actually put that in your calculator as a fraction like that, so I'll write it like that this time around, divided by 365 raised to the 1.75 times 365. Put that in your calculator and you get the magic number. I'll actually throw it in the calculator just so you can have something to verify. Okay, let me grab a calculator. We said 1,000 times 1 plus 0.04 divided by 365 raised to the negative 1.75 times 365. So we need to invest $932.40. Ooh, look how I lost my negative sign. I put it in the calculator though. So $932.40 is how much you need to invest right now if you want to get $1,000 in a year, almost 2 years. That means you ain't getting nothing but $67.60 after waiting almost 2 years. Don't waste your time. Continuous compounding, and this is an error in the formula there. That should say raised to the RT, not NT. So continuous compounding is future value equals present value times E raised to the RT. Alright, so you will never see an N in a continuous compounding formula. It's compounding all the time. Alright, so find the amount that results from investing $2,000. So you're investing present value. You invest in $2,000 at an annual rate of 8%, interest rate of 8%. Convert that interest rate to a decimal, and you're going to do that for 1 year. So, like, what's that amount? So we have $2,000. I didn't mean to put that. Can I get me an eraser? Thank you. You have $2,000 raised to the 0.08 times the number of years. Let's toss that in the calculator. 2,000 times, not times, raised to the 0.08 times, I think it was 1 year. Oh my goodness, where's my E? This guy over here tripping. Let me just clean that up. I can't believe I didn't put my E into the formula. Ooh. Future value equals the present value of $2,000 times E raised to the 0.08 times 1. Oh, that'd look a whole lot better. So 2,000 times E, and E is located over your division symbol, or you can use the E that's attached to the natural log because it's going to automatically put that one to an exponent. 0.08 times 1. There we go, $2,166.57. That's looking much better. $2,166.57. Alright, team. That concludes this lesson. See you next time, my math people.